Last class, we learned what recursion is and the 80-40 the base case, the recursive case, and the call stack. Today, we make recursion something you can actually see. Because here is the thing that trips people up. Recursion is genuinely hard to trace in your head. Once a function calls itself, which branches into more calls, your mind quickly loses the thread. But recursion is remarkably easy to see, and A212, if you draw the right picture. And there are two pictures that between them explain everything. The recursion tree shows you the whole computation at once, every call and how they branch. The call stack shows you how the computer actually runs it, one path at a time. Master these two mental models, and recursion stops being magic. You will be able to look at any recursive function and read its speed, its memory use, and its waste right off the page. This skill is what turns hard recursive problems into ones you can reason about calmly. So let us learn to see recursion. Here is what we will understand today. First, why drawing recursion beats tracing it in your head. Second, the recursion tree. Third, the call stack, revisited more deeply. Fourth, how the tree and the stack relate. Fifth, how branching drives the cost. And sixth, how depth drives memory. Let us begin. Let us start with a confession that will make you feel better about recursion. Even experienced programmers cannot reliably trace a non-trivial recursion purely in their heads. The moment a function calls itself a few levels deep, and especially when it branches into multiple calls, the mental bookkeeping explodes, and 8/12, you lose track of which call you are in, what it is waiting for, and what has returned. If you have ever felt lost trying to follow recursive code line by line, that is not a failing, it is just the wrong method. The right method is to draw it. On paper or in your mind ND39, SI as a diagram, recursion becomes obvious. The two pictures we will learn, an 8hen 2ID to true ID, the tree and the stack, and 8hen 2ID 2ID. Take the tangle in your head and lay it out flat where you can read it. What was confusing becomes something you can point at. So the shift I want you to make is this. Stop trying to simulate recursion step by step in your head and start drawing it. Professionals reach for a diagram almost automatically when a recursion gets tricky. It is faster, it is clearer, and it reveals things an 8/12, like hidden inefficiency and 8/12, that pure tracing hides. Seeing beats simulating? So the takeaway? Recursion is hard to trace in your head, but easy to see. So draw it, an A212. The recursion tree and the call stack turn a confusing tangle into a picture you can read at a glance. The first picture is the recursion tree, and it captures the entire computation in one diagram. The rule for drawing it is beautifully simple. Each call is a node. You write down the call, and A212, say, the function with a particular input, and A212, as a single dot or box. That node represents one invocation of the function, one moment of it running. And the calls that a node makes become its children. When a call recurses an 80-112, when it calls the function again an 80-112, you draw those new calls as nodes hanging beneath it, connected by lines. The top call is the root. Its recursive calls branch downward. Their recursive calls branch further, and so on, until you reach the base cases at the bottom, which have no children because they do not recurse. What you end up with is the whole shape of the computation, laid out at once. You can see every call that will ever happen, how they relate as parents and children, how wide the tree spreads, and how deep it goes. Nothing is hidden in your head anymore. N812. It is all on the page. And, as we will see, the shape of that tree tells you almost everything about how the recursion behaves. So, the takeaway, the recursion tree draws every call as a node and the calls it makes as its children, from the root down to the base cases and A212, giving you the entire computation as a single picture you can read. The tree shows all the calls. The second picture, the call stack, shows how the computer actually executes them, and A250, and the two are complementary. As the program runs, each call is pushed onto the top of the stack and paused there, waiting. When the root calls a child, the root is frozen and the child goes on top. If the child calls its own child, the child freezes and the grandchild goes on top. The stack grows downward into the tree along one path, each call suspended, waiting for the one above it to finish. The base case is what stops the descent. When a call hits the base case, it does not push anything new any A2 valve. It simply returns its answer. This is the first call to actually complete at the bottom of the current path. Then the stack unwinds. With the base case returned, the call that was waiting for its resumes finishes its work and pops off the stack an A2 or 12, which lets the call beneath its resume, and so on, popping back up. The computer never holds the whole tree at once. It walks it one path at a time, pushing down to a base case and popping back up over and over until the root finally returns. So the takeaway, the call stack shows how the machine runs the recursion NA2112. Each call is pushed and paused. The base case returns first. Then each paused call resumes and pops off NA2112, walking the tree one path at a time. These two pictures describe the same recursion, so let us be precise about how they differ. Because using the right one at the right time is the whole skill. The tree shows the full shape and A212, every single call that will ever be made, and how they all branch. It is the complete map of the computation, existing all at once on your page, even though the calls happen at different times. It is what you look at to understand the total amount of work. The stack shows one path at a time, and A212, just the calls that are currently active, frozen and waiting, at one instant during execution. It is never the whole tree, it is the single chain from the root down to whatever call is running right now. It is what is really in the computer ND signing registers memory at that moment. The keying way to hold both, the tree is the whole map, and the stack is where you are on it. If you trace a finger from the root down one branch to a node, that finger in E39 C path is what the stack contains when that node is running. The tree is space laid out. The stack is a moment in time. Use the tree to reason about total work and the stack to reason about what is live right now. So the takeaway, the tree is the whole map of every call and how they branch, while the stack is the single active path and A200 tool fall. Where you currently are on that map, an A200 tool fall, so use the tree for total work and the stack for what is live at any moment. Now, the payoff and 8085, the recursion tree makes something visible that is otherwise easy to miss, the true cost of a recursion, decided by how much it branches. If each call makes just one recursive call, the tree is a straight line downward and 812 pole, no branching, one node per level. That is linear work. The total number of calls is just the depth. A countdown, a simple list traversal, factorial from last class, and 80 to 100 of these are straight line recursions and they are cheap. The tree is a stick. But if each call makes two recursive calls, the tree branches and 8 to 112, and it explodes. One call becomes 2, 2 become 4, 4 become 8, doubling at every level. That is exponential work. The number of nodes roughly doubles with each level of depth, so even a modest depth means an enormous number of calls. The tree is a dense triangle, and it goes terrifyingly fast. This is the single most important thing the tree reveals. How many children each node makes determines whether your recursion is fast or ruinous. One child is linear and fine. 2 children is exponential and often disastrous for anything but small inputs. You cannot see this from the code alone, and 8 to 112, 2 innocent-looking recursive calls hide an exponential explosion, and 8 to 112, but the tree shows it instantly. So the takeaway, the branching factor drives the cost, and 82 while if each call makes one child, the work is linear. But if it makes 2, the tree doubles at every level, and the work is exponential, and 82 while, and the recursion tree makes that difference impossible to miss. Let us make this concrete with the most famous example of recursion gone wrong, and A212, the naive Fibonacci. The naive recursive Fibonacci computes each number by calling itself twice and 8 high into once for the previous number and once for the one before that and 8 high into how, and adding the results. 2 recursive calls per step. From what we just learned, you already know what that means. The tree branches and the work is exponential. But it gets worse, and the tree shows exactly why. Draw the tree and you see the same values being computed over and over again. To find the 10th Fibonacci number, the same smaller Fibonacci numbers are recalculated a staggering number of times, in different branches, each from scratch. The tree is full of identical subtrees, computed independently, wasting enormous effort. That redundancy and A2A2 solve, recomputing the same sub-problems again and again, and A2A2 solve is invisible in the tidy-looking code but glaring in the tree. This is why naive Fibonacci is painfully, famously slow, and it is a perfect lesson. The recursion tree does not just tell you a recursion is exponential. It shows you the wasted, repeated work causing it. And once you can see repeated sub-problems in a tree, you've spotted exactly the situation that later techniques and 82 valve, like memoization and dynamic programming and 82 valve, are designed to fix. So the takeaway, naive Fibonacci calls itself twice each step and recomputes the same values over and over, and 82A12, and drawing its tree exposes both the exponential blowup and the repeated sub-problems, which is precisely the waste that optimization later removes. We have used the tree to understand time. Now let us use the stack to understand memory, because recursion has a space cost that beginners often forget. The memory a recursion uses is set by the depth of the stack and A212, how far down the longest active path goes. Remember, the stack only ever holds one path at a time, not the whole tree. So the memory cost is not the total number of calls, but the maximum depth the stack ever reaches, and A2112, the length of the longest branch from root to base. A wide tree can still be cheap in memory if it is shallow, because only one path is live at once. But if a recursion goes very deep and A12, a very long chain of calls before reaching a base case and A12, the stack grows very tall and it can exceed the limited space the system gives it. That is the stack overflow we met last class. And now you can see its cause precisely. Too great a depth, too long a single path. So the two costs come from two different features of the picture. Time comes from the total number of nodes in the tree, and A212, driven by branching. Memory comes from the depth of the stack, and AT40, the longest path. Our recursion can be cheap in one and expensive in the other, and separating them is key to reasoning correctly. So the takeaway, memory use equals the stack in 39's maximum depth and A244. The longest active path from root to base in A244, not the total number of calls. And if that depth gets too great, the stack overflows. Time comes from branching, memory from depth. Let us turn all of this into a repeatable method and 8 3 steps to analyze any recursion you meet. First, draw the tree, write the top call as the root, and draw the recursive calls it makes as children, level by level, down to the base cases. Even a rough sketch of the first few levels usually reveals the shape and 80-1, 12 a straight line or branching. Second, count the work. The total time is roughly the number of nodes in the tree times the work done at each node. A straight line tree has few nodes and is linear. A branching tree has many and is exponential. The shape you just drew answers the time question directly. And third, check the depth. Find the longest path from root to base and the 81 to how. That depth is the memory the stack will use, and a warning sign for stack overflow if it is large. With those 3 steps and 80-80-80 off, draw, count the nodes for time, measure the depth for memory, and 80-80 off, you can size up the entire cost of a recursion without running it. The tree gives you time, the stack depth gives you memory. Together they give you the whole picture. So the takeaway, to analyze any recursion, draw the tree, count its nodes for the time cost, and measure its depth for the memory cost, and 81-2, tree for time, stack depth for memory, and you have read the whole cost at a glance. Let us close with the habits that make these pictures a reflex rather than a one-off exercise. First, draw the tree before judging a recursion N209's speed. Never assume a recursive function is efficient just because it is short. Two innocent recursive calls can hide an exponential explosion, and only the tree reveals it. A quick sketch before you trust the code will save you from nasty surprises on large inputs. Second, watch for repeated subproblems in the tree. If you see the same call appearing again and again across different branches and A2 full, as in Fibonacci and A2 full, that is a flashing sign that the recursion is wasting work and a cue that it can later be optimized by remembering results instead of recomputing them. Spotting this is the first step toward dynamic programming. And third, mind the depth. Ask how deep the recursion can go on the largest realistic input and A200 tool, because a very deep recursion risks overflowing the stack, and you want to know that before it clashes in production, not after. Draw for speed, look for repetition, and check the depth. 3 habits that keep recursion safe and fast. So the takeaway? Sketch the tree before trusting a recursion and 39s speed. Watch for repeated subproblems as a signal to optimize, and check the depth for overflow risk, and 8212. Make these 3 a reflex and recursion hose, no surprises. Let us gather the whole class in one breath. Draw recursion. Dawn and T9, T-trace it in your head, and 81 T hand 1. It is hard to simulate but easy to see. The recursion tree draws each call as a node and its calls as children. The call stack pushes and pauses calls, returns the base first, then pops back up. The tree is the whole map. The stack is your current path on it. Branching drives cost and A2 hen 2 and 12. One child is linear, 2 children is exponential. And depth drives memory and 84 to Paul. The longest path is the memory used, and 2 deep overflows. Next class and 8212. Arrays, the simple data structure of all. One idea at a time. That is how you see recursion and 84 fall. The tree for the whole computation and its cost in time. The stack for how it really runs and its cost in memory. Draw those 2 pictures, and a recursive function stops being an opaque piece of magic and becomes something you can read, fast or slow, cheap or wasteful, safe or overflow prone, all visible before you ever run it. Carry these pictures with you, and the recursive problems ahead and 82 towel, searching, sorting, trees, dynamic programming, and 82 towel will feel far less daunting. We will see you in the next class.